Good afternoon. Hope you all have a great lunch. Yeah. And thanks a lot for the invitations to share our previous experience so that we can try to bridge the coastal ocean process with the global climate system. Hopefully this will be a talk which we can talk from the morning talk. We have focused most on the global ocean part, and this afternoon we are talking more about the regional part and some challenges we may be facing with. Okay, so I will bring up some of the challenging work, okay, related to the non-hydrostatic factors, or also complex topography, also some unresolved process we may think of so far. And then I will talk a little bit about the downscaling approach, how to move from global to coastal, then also coastal, how to global. So that will relate to a lot of multi-domains and multi-dynamics will be involved. Then I will bring maybe a framework a little bit about the multi-scale ocean and atmosphere coupling model system, which that could be. Okay, so I will just start from the regional part. Around like 20 years ago, we started using the large GID simulations, as you may know, which we have the three-dimensional numerical modeling LES so that we can model the coastal upwelling events. Particularly if we can look at with capes or without capes, we can tell if for a typical coastal upwelling system, we can get this kind of instability like filament, also we call it fish hook structures. But this kind of structure cannot be easy to think with a cape. That means the coastal topography actually can play some very important roles. So these capes can also very similar to this when we move to the regional models, we can have this kind of phenomenon so that this kind of filaments so that we can try to model it correctly within a regional model. And the resolutions for this model is around like 1 kilometers for the regional part. But this kind of issues is how that's important. Okay, so easiest way to look at is to look at the non-hydrostatic effects associated with this kind of like topography-driven upwellings. Then, so we can compare, look at, we call it the non-hydrostatic factors, compare the ratios between the non-hydrostatic turns and the hydrostatic turns, looking at the ratios of that. As you can tell, there are two locations which we can see very strong non-hydrostatic effects. One is within the Monterey submarine canyons, so very steep topography that somewhere we can see from the deep ocean have very strong point. The other place is this part, we call it the point surf. It's a surf ridge, a very shallow place. So both deeper canyons or very shallow location, we can also find very important non-hydrostatic effects this moment. So in general, in fact, we have to consider the non-hydrostatic effects and the interaction with the complex topography that can change the instability we thought, and also the filament structures, and also the fish hood structures like structure in 3D. So this structure is something we cannot miss. Otherwise, the simulation will get some issues. Okay. Then here comes to another example is for the high resolutions. The need of the high resolution is, for example, if we want to model the Mediterranean Sea and also North Atlantic all together, what can we do? So the easiest way to do is this is based on a very simple three-dimensional ocean model. But if for the open ocean, we use coarser grid resolution. But for Mediterranean seas, we use around like 1/8 degrees. But between land, there's the Strait of Gibraltar. We use high resolutions, around like 4 kilometers resolutions, and to try to resolve this dynamic associated with this exchange. So what's important of this Strait of Gibraltar's domain is near the upper oceans part, we can see the North Atlantic Ocean will move through the Mediterranean Sea, and we can see very clear western Barents gyres, and also a lot of sub-mesoscale features. Okay, and this kind of features are something very important for the upper oceans. But at the left side, so basically we have to resolve the strait exchange and also the mesoscale and the submesoscale features. This is also very important for the coastal dynamic. Okay. But under the sub-upper oceans, there's also deep ocean. There's very common things we call the Mediterranean, the overflow waters may come from the Mediterranean seas and move into the North Atlantic. And this is the temperature at around like 100 meters, 100 meters. We can tell this kind of temperature distribution. We can very strong warm waters will come into the North Atlantic. Indeed, the overflow waters can actually affect it because when it moves to the North Atlantic, turn right, can affect the AMAC and also North Atlantic circulation layers. So this overflow is something we cannot ignore in the model. However, in a climate model, this kind of overflow actually is parameterized in climate model. So this kind of phenomenon need to be fully resolved in general. The other things that I want to bring up is the strengthening of the internal tide. This morning, I know we already heard some of the talks related to the typhoons or tropical cyclones impacts. But most of the tropical cyclone, we are saying, oh, tropical cyclone can bring up a lot of mixing to the ocean. So generally, for example, in South China Sea, we heard a lot of previous study talking about the internal tide will become weakened, and in particular, also the internal wave will be weakened because of the increase of the mixing. However, from real observation, we actually observed several events. This is one example for Typhoon Nabat. We have observation around like near the Dongshan Island over here. We found that the internal wave in that area just could be enhanced due to the passage of the typhoons. Therefore, we just focus on look at the dynamic, what happens over here. In general, later on, we found that because of the typhoon, the cyclonic circulations, it will generate also the downwelling at the front of the left-hand side, okay, left-hand side of this typhoon for the oceans. It can deepen and also sharpening the thermocline. That can weaken the nearly inertial wave, which can reduce the mixing. And this mixing can actually enhance the stratifications over there, just somewhere near where the internal wave generation tide locations. So this story actually, the investigation actually tells us that the internal tides and also internal waves actually is something we have to consider in an Earth system model, because it can sometimes not only weakening its effect, but it can amplify and feedback, maybe potentially feedback to the atmosphere later on. Okay, so this is something very interesting from observational viewpoint initially, but later on we try to use the ocean model to verify the dynamic behind. Then I will talk briefly about the dynamic downscaling. That's something we are doing right now. I think in the last maybe 10 to 20 years, everybody is doing this climate downscalings. For example, we are running a project, the current change in the Western North Pacific. The left is the course resolution, which is based on the Thai ESM. It's based on the 1 kilometer Earth system models we are using now. Then the right one, actually you can tell the features significant large difference between them. This is based on a climate downscalings at around like 9 kilometers, of course. But in order to get these models running well, in fact, we need to force these oceans by another around like 25 degrees atmosphere forcing to get this kind of more accurate crucial behavior. One example is we can tell this kind of, we call it crucial loop currents intrusions. It can intrude into the Luzon Strait, but this cannot never be seen from the Earth system models here. Another is you can tell very strong, this is the current strength, can very strong crucial change, but in the coarse resolution, the crucial is very broad, very broad. Okay, and without any deformations. For example, for high resolution, we can see this kind of intrusions into the East China Sea sometimes. So this kind of feature is something we cannot really find from the Earth system model. So the very important key is the multi-scale dynamic need to be considered in downscaling. So it's very difficult to jump directly from like 1 degree resolution climate model to like 10 kilometers or even like kilometers. We have to through some kind of, through like maybe 25 kilometers first and then back to 10 kilometers. Okay, so here I'm going to talk a little bit briefly about the multi-dynamic, how to model it. In general, this is something I believe some of team members here use like ICOM coast model. So it's something very similar. But we have to think about some of approach, like this morning's talk. Some groups are using like the MPAS oceans. They use unstructured grid configuration. However, we need to consider important things, the efficiency. Okay, because our Earth system model is already too complicated enough. So in terms of the coupling between the coarse grid and the high resolution grid, efficiency is very important. So the algorithms, we believe we must not take too much computational resource. And it needs to be very relatively simple to program. But for the MPAS ocean, that's one example. Sometimes the computational actually too much, at least for us. And the other things we have to consider is the conservation things. One important thing is flux need to be conserved. Okay, also a very important thing is we have to keep the minimal dissipations. Okay. And also, no appearance of unrealistic value, of course, like salinity, we can never get the negative values. But if you know, if we put river runoff, put in, sometimes we'll get negative. But I will talk about that later. And also, we have to ensure the stabilities of your models. So a very smart approach is probably it's better to use this kind of nesting or downscaling, so that we can match for the coarse resolution and high resolution, trying to match them, align on the same grid point, so that we can conserve the total mass or momentums at the same time. But if we are using this kind of more mechanical engineering type of approach, maybe not quite recommended because the computational cost is too complicated. So in general, what we want to say is we want to to try to model the multi-scale dynamic. So a potential approach could be, okay, if we can run a global models, but for Pacific Ocean, we can separate into several domains, and for North Atlantic domain, we can also separate into several domains, so that we can try to model for certain regions. We see, okay, those regions we need high resolution here, so we use the high resolution. For some regions, we think, well, the coastal process may not be so important, so we can use some not so important, not so high resolutions. So that can save our computational cost significantly. So the next step I'm going to talk briefly is about the dynamic downscaling. I will just give one example of this. Is based on a very interesting work we did previously by quantitatively risk assessment of climate change impacts on underwater cultural heritage. All right. So basically, we downscale from the 1 kilometer, so TropEcS, which is an Earth system model, is around like 1 kilometer. We downscaling to 9 kilometers, I just mentioned. Then we put to the 2 kilometer in Penghu regions, the resolution, then to the Magong River and 100 meter resolution, down to the 5 meters resolution at the end. Okay, so through this dynamic downscaling, what can we learn? Right here is just what we want to focus, because we want to look at the underwater, the culture of which is worshipped. Guangbing worship just think probably 120 years ago in Taiwan Strait. We want to understand how it is suspicious to the environmental factors that can including the erosion, score, and the corrosion. So if we look at the high resolution, extremely high, like 5 meters resolution things to resolve this reef, okay, you can tell a lot of vortex dynamic in this area, particularly very strong submesoscale features. Also, vortex dynamics actually matter when we go to the 5 meters resolutions. And this is something within how does it matters. Okay, if we further look at the future projections, okay, the top is by the high resolution. This is from the 9 kilometers TropEcS run simulations. And this is after downscaling to 5 meters. Okay, if you further look at the feature, the temperatures, behavior, temperature different from winter, spring, and summer and autumn, you can tell they are totally different. The main reason is when we include the higher resolutions of topographies here, you can, for example, the temperature increase, comparing the future, just use the future and the minus current difference, okay? This is around like 1.2 degrees C, and this is around like 0.8 degrees. So it increased around 1.2 degrees C in winters and 0.8 in summer times. Okay, but when we look at the kilometers resolutions results, okay, the increase of temperature, the sea surface temperature is around 1.4. Okay, the scale over here and here, they are all the same. Okay, it's around 1.4. So actually, why this temperature warming can be reduced in the even high resolutions, mainly because enhance the topographical upwelling. Okay, it can enhance the mixing, so the coastal upwelling can reduce this kind of future the warmings from the kilometer simulations. So that's something we have to notice, that if we go to kilometer scales, well, maybe we can capture some subscale meters features, but if we even go further down based on the same information, okay, we found the simulation can get something different. Okay, so that's something we have to be aware that the consequence will differ. Okay, even this physical and also later on we can affect the biological, ecologically, even later on socio-economically. Because why we are interested in this region is because this is the fishery area, very, very important fishery areas in Taiwan. Okay, so Besides that, so I will bring another issue is related to the atmosphere and ocean coupling framework. Okay, this is one example. By comparing the El Nino events, okay, and the La Nina events, we can find that it has a by running a couple model simulations, run in the El Nino event, we can find quite weaker certification in the Pacific westward propagation Rossby wave, and also mesoscale eddies and corrosion intrusion. But the circulations looks quite different when we look at the El Nino event, the La Nina events. So indeed, actually, we really need a complete, if we want to focus on regional part, well, the boundary condition is one issue, but we also need a comprehensive the regional ocean and the atmosphere coupling so that we can include both the larger scale climate patterns go into our regional circulation more appropriately. Okay. Another good example is the atmosphere, the dust, okay, the aerosol dust. So the right panels actually show the aerosols AOD concentration. I think people are talking about this aerosols can affect the global warming and reduce the sea surface temperature. But when we run the couple regional high resolutions, okay, high resolution couple models, we found that, well, it's not necessary everywhere will be cooler for sea surface temperature. For some areas in the tropical regions, also subtropical regions, we can still get some kind of warming effects. Okay, so actually this kind of change of warming effects comes not purely directly from the aerosols impacts. Because of the change of atmosphere circulations and the SST, it's not only the direct solar radiation flux, so there are some indirect can interact with the ocean, then feedback. One example is the tropical instability wave. We can see it over here. Okay, this wave later on, I think in a later section we'll have there's a speaker will talk about that. But and also the mesoscale eddies in this area, in these tropical areas. So that's kind of like a tropical instability wave. The instability can generate also upwellings over in these areas. Okay, so these kind of the combination of this ocean process can actually make the whole simulation more complicated than we thought by just purely the aerosols direct impacts only. Okay, so these are how we are looking at from the global climate downscaling to regional process. But here I will talk a little bit about the upscaling of the coastal process. One key point in the most of the current Earth system model, we use the improve the augment precipitation approach. So we include adding more river runoff to the model system. But one approach, a simple approach to consider this coastal process is to just change the inflow from the surface to the lateral boundary. That's one improvement. The other approach is more complicated. Like this morning, the speaker has to talk about the estuary box model. So after we have this kind of surface runoff, the surface runoff can move the water into how this runoff will move into the ocean is the state of the art at this moment for the Earth system model. If we want to correctly represent the whole process and the mixings, an estuary box model actually is a very important part, which we can consider the estuary exchange so that we may not necessarily get the negative salinity I just mentioned from the Earth system models sometimes. Otherwise, normally the way we did it, just use the dissipation to diffuse it out, but that's not something we want. But after we put into the estuary box model, however, there are several shelf break processes. For example, upwelling is one important one. And the other is like the wind relaxations periods. That's also something important. So indeed, in order to upscale back to the global couple models, maybe another wind mixing plumes is also a very important process, okay, from the coastal perspective, very important process we should consider. So another shelf box model may be also necessary when we move it to that. I will explain that a little bit later. So just quickly talk a little bit about the S3 box model. Is we are trying to parameterize. That's what we are saying, to parameterize. But this kind of parameter is based on some physics. We consider the continuity equations and the density balance and potential energy balance and also momentum balance within that, so that we can consider the estuary exchange. So the open ocean water can move into the land, and also the land, we have the river runoff from the upper layer can move back to the oceans itself. By looking at the different, we are treating different rivers differently. So for example, looking at like Changjiang, Mississippi River, Hudson River, we have to use different parameters for these kind of different rivers. Okay, so based on this kind of setup, we can find that when we comparing a simulation with this estuary box model and without estuary box model, we can see significant difference in the Amazon rivers and even like Columbia rivers. We can see large difference right here. And how this is important? Actually, this can actually affect the surface, the chlorophylls. So we can tell it can affect the ecosystem and be biogeochemistry's impacts later on. So this is an example if we look at the surface chlorophylls by taking the difference between the EBM and minus the standard deviation. We can tell a lot of difference in the tropical, this is where we can see the strong tropical instability wave, Gulf Stream and crucials, the western boundary current stuff. So actually, we can see a lot of difference over here. Then also, I mentioned, after we got this S3 box model, we are trying to parameterize some of the river input. Okay, we mix up all of these waters, but we still have to consider some unresolved soft break process. One example is the buoyancy-driven situation. We have to consider buoyancy-driven situation, upwelling wind. It can change or move the water, the plume offshore further. Wind relax, it can move it back. So by consider this, this is actually more complicated work. So I just give you one example for the offline shelf box model. Is based on the wrong simulations. Is this? So you can tell from the simulation, this kind of coastal plume, okay, it can move back and forth. Okay, depends on your atmosphere wind and the forcings at all. So this kind of information need to be within the Earth sensor model, particularly in the global scale. It can feedback to global scale so that we can have better flux corrections. Okay, so this is something we really have to care about from the downscaling and upscaling part. But so finally, I will just bring up the one potential framework. Okay, this is based on an Earth system model we are building right now. Is by combining the regional model and the global model all together. So basically, for the global model, we run this all simulation by adding the ocean and atmosphere all together. And then we also have a regional model, also regional couple ocean and atmosphere model all together. And the framework we are having here is because we are trying to make it more operationally. So in the regular times, we are running smaller domains for Taiwan regions. But if, for example, there's a typhoons coming or some specific events coming, we can run for a larger domains, and this kind of adjustment can be done automatically, can change itself. And also this kind of block can be changed and can be put onto anywhere in the world. Okay, and right now we are actually just ahead of this is additional things. We are also change This is an example we are showing by using different processes. As you can tell, this is the timing. This is the course numbers we are using. Of course, this morning, the course number we talk about a certain number is around 10,000 or more. But right now, because of the lack of computational resource, we only have like at most more than around 2,000 cores. That's why we do it normally from operational result. But we can tell the speed up is good. The timing, when we do this model for 24 hours, we can shrink it. We can reduce the time to several minutes. So this is good for us to simulate the whole simulation. And we are also trying another is 8 GPU. We are porting this to the GPU at some point, but still ongoing. So let's give you a good example why this kind of coupling will be important. This is comparing the couple model and uncoupled model for doing the S2S forecast. The co-model system we have is this one, and uncoupled system is this one. So we can tell the predictability scale actually increased significantly this moment. And also, if we look at the co-search events, this is one example for 2024, January. Around like 3 weeks ago, we can actually the model actually can already predict this kind of decreasing trend from the couple model results, but it's not quite clearly fit. But around like 2 weeks before, we can really see this kind of change. All of the predictions can see this kind of change significantly well. And even like the last 1 week ago, we can predict this co-event pretty well. So let's tell you that this is very important part. The last things I want to bring up is the codiff, the AI, how AI can help this dynamic downscaling. There's something we are doing based on the codiff. Is if you went to like Jason Huang's presentation in NVIDIA's talk, you can tell there's one slide which focuses mainly on the Taiwan. So basically, we provide the data. So we're trying to use the regional wolf model result we have to train their model to get the better course resolution. But that cannot be fully explain the dynamic completely. So I will just stop here for any questions. Thank you.